So hi everyone, my name is Stan, and I'll tell you about my master's project on interpretable anomaly detection. So the aim of the project is to look at video from CCTV cameras and spot anomalies, that is uncommon or unusual behaviors or objects, while automatically generating explanations of why they were found to be anomalous. So for example, in a video like this, we would like to spot anomalous frames and explain that they are due to people pushing each other. Other examples of anomalies can include people fighting, people running, picking up bags, throwing bags, or others, such as a leaving bag unattended in a train station or a car driving on a pavement. Anomaly detection has important applications in video surveillance, where you want to spot unusual behavior and intervene if it's dangerous. In autonomous driving, a car has to hypothesize about the future of the scene it's going to encounter and detect any deviations from it. So for example, when a pedestrian falls on the pavement. In my opinion, explanations are absolutely essential for the task of anomaly detection because systems used in public settings, for example, in video surveillance, have to be transparent in order to prevent any bias, for example, racial bias. Secondly, the appropriate response to detected anomalies depends on its nature and severity. For example, when a person is walking in the wrong area in the train station, the guards should probably just stay vigilant, but if they're carrying a gun, they probably have to intervene immediately. Interpretable anomaly detection is challenging because the most important anomalies involve complex interactions between people and objects. Second challenge lies in the fact that deep neural networks at the forefront of this problem are usually a black box and are not interpretable. Indeed, there's only one work, to the best of my knowledge, that describes the detected anomalies. However, it ignores interactions between objects, which can be a crucial source of anomalies. Moreover, it's still not fully explainable because the features, the input it uses to detect anomalies cannot be interpreted, so the system is not fully transparent. The second challenge lies in the fact that there is currently no benchmark for the task of anomaly explanation. And even if our system produced anomaly explanations, we wouldn't be able to currently measure how good it is. Other anomaly detection methods use deep feature representations and are effectively a black box and cannot be interpreted. To tackle these shortcomings, my project starts by developing a new dataset for benchmarking anomaly explanations, to evaluate how good my systems are, and also to push further research in this area. I then tackle the problem of explainability by developing an explainable prototype that uses interactions directly to detect anomalies. The prototype is then seen to have some shortcomings, which I address by developing a second, more robust, but still interpretable method. In the presentation today, I will tell you about the dataset I developed, about the prototype and its shortcomings, and how I address them by developing a second, more robust, but still interpretable method. I will quantitatively analyze both methods and then draw some conclusions. The dataset I built was created by taking anomalous frames, so frames of anomalous events from existing public datasets, and giving them two tags, giving each of these frames two tags. These tags, the first tag is a coarse explanation of the anomaly, whether it's due to an anomalous action, object, or location. The second tag is a fine-grained explanation of the anomalous event. For example, in this case, it would be running. The whole dataset consists of a wide variety of different anomalous events, ranging from a person driving a motorcycle on the pavement to a person practicing martial arts, people fighting, or someone hitting another person with a bag. The interpretable prototype I developed is developed using two motivations. The first one is we want to use interactions explicitly for the task of anomaly detection because I hypothesized that they are an important source of anomalies. The second motivation is to use deep neural networks to form feature vectors as an input to then traditional probabilistic modeling to provide interpretability. By using deep neural networks, we can leverage their perceptive abilities, and the traditional probabilistic modeling will give us interpretability. So in more detail, I take an input frame and I detect all objects in the scene. I can detect anomalies by building a human object interaction vector for each pair of objects in the scene. The Hobby vector consists of the different classes of interactions between the two objects, the object category probabilities, and the person bounding box size, which implicitly encodes the location of the person in the scene. The human-object interaction vector is inferred using deep neural networks and is then input to a probabilistic modeling model, namely a Gaussian mixture model, to detect anomalies. For any detected anomaly, I can then interpret it by direct inspection of the Hoey vector. I can also explain what made it anomalous, so which of the three parts of the Hoey vector was responsible for flagging it up as an anomaly. Using the Gaussian mixture model, in this case, it would be the object, the bicycle, because we haven't seen any bicycles in training. So under this probabilistic model, bicycles are an unusual and unlikely event, and this model finds it as an anomaly. The system is able to detect and explain a wide range of anomalies with anomalous interactions, objects, or locations. And indeed, the results we get and this method and datasets were accepted to a CVPR workshop, and CVPR is one of the biggest machine learning conferences in the world. The system is, however, not perfect because failures in object detection will lead to downstream failures. I will now show you some examples. First of all, failures in object detection when we detect spurious objects lead to false positives, that is flagging up an event as anomalous when indeed it's just normal, because we detect some spurious object, so a cup or a fire hydrant. Failures in object detection can also lead to false negatives where we fail to identify an abnormal frame. For example, here the person is throwing a bag, and our object detector does not detect the bag itself because the bag is in an unusual location. So usually people are wearing or holding bags. Here a person is throwing it. The bag is also blurry.
It looks like there's a connection issue with the Stan. So should we wait for a minute or so and see whether he can come back and finish his talk? Okay, he's coming back.
Hi, sorry, apologies, my internet just failed.
No, this
sorry for that.
No worries, and I think you can continue.
Yeah, I'll just continue where I left off. Yeah, so the second shortcoming of this method is that it completely ignores the temporal context, which could be useful for extracting information that could be used for detecting or explaining anomalies. To address those shortcomings, I developed a second, more robust method that takes an input of 5 consecutive frames and passes them through a deep neural network that is trained to predict the future next frame. This network is trained on normal events only, and then in testing, we can compare the output to the ground truth next frame to form a saliency map of per pixel prediction error, which then can be used to detect anomalies, because we assume that by training the neural network only on normal events, it will make bigger mistakes when it tries to predict abnormal events. And this prediction error can be a signal that we use to detect anomalies. I then plug the saliency map and the ground truth next frame into an explainability module, which I will explain later. Note that this method does not require object detection as a pre-processing step to detect anomalies, and it can also extract the temporal information by taking the frame sequence as an input, therefore addressing the shortcomings of the previous method, but still being explainable. The architecture of the deep neural network is a standard architecture used in the task of anomaly detection, a VQU-Net. And this architecture can also be trained for single frame reconstruction. So instead of predicting a future frame, We just input a single frame and try to get the same frame back at the output. But for that task, we remove the skip connections, so the green arrows, because otherwise the network could simply copy the inputs to the outputs. VQU-Net generalizes really well. Some qualitative analysis shows that it can produce a wide variety of frames, and it generalizes really well to unseen examples. However, some more analysis shows that it generalizes maybe even a bit too well, because it's able to reconstruct abnormal events. Here is an example of where passing a bike and a cyclist on it through the network results in a correct reconstruction. So you can still see the outline of the bicycle and the cyclist. This is an abnormal event. So ideally, we would like the network to completely get rid of the cyclist and the bicycle and to be ordered to detect this, to be able to detect this anomaly. So to address the shortcomings, I modify the architecture by using a vector, by inserting a vector quantizer module at the bottleneck. I simply just modify the architecture, making this a novel architecture for the task of anomaly detection. This new model, the vector quantizer, restricts the feature map to be a combination of normal features only seen in training, therefore imposing quite a strong limitation. And this forces the network to only be able to reconstruct normal events. I will now show you the results, the result that Vector Quantizer has on the reconstructions of abnormal events. This is probably the most important slide of the whole presentation. So when taking an input abnormal frame, without the Vector Quantizer, the baseline network from the literature is producing a blurry version of the truck. It's blurry, but you can still clearly see the outline. With the Vector Quantizer, my network completely gets rid of the truck and replaces it with person-like blobs. In this example, a cyclist and the bike you've seen on one of the previous slides is completely replaced with a pedestrian by my network. Here we completely remove a person bending over to pick up a bag, and here we remove a person who's cycling on a bicycle with a pedestrian. So this is advantageous for the task of anomaly detection because ideally the model should only be able to reconstruct normal frames. And we want to be able to guarantee that it won't be able to reconstruct abnormal events because we want big mistakes and we want to be able to guarantee that if there's an abnormal event, for example, a person holding a gun, then we will definitely detect it. And these examples show that with my novelty, the network is much more likely to do so. I will now show you how we can also use this network for explanations. To do that, we take the input of 5 consecutive frames and pass them through VQU-Net, so the same architecture as the same neural network as I've shown before, to form the per pixel prediction error saliency map. By taking them, we can then take the ground truth next frame and pass it through state-of-the-art object detection and the action recognition networks. These are one of the best methods available in current literature, and they output a set of bounding boxes and corresponding labels. So for example, the bounding boxes you see on the examples here, and labels, for example, a bicycle, a person, a handbag, walking, running, etc. Then we can sum the per pixel prediction error within each bounding box and threshold them to obtain a set of anomalous bounding boxes. And the tags, the labels associated with those bounded boxes can then be used as anomaly explanations. Here are some examples of correctly detected and explained anomalies, where we detect anomalies due to people riding a bicycle on the pavement, a truck driving on the pavement, someone practicing martial arts, or someone bending or bowing at the waist. Quantitatively, I can compare my methods to state-of-the-art methods on one of the commonly used metrics, and this metric, the bigger, the better. As you can see, my methods, both the prototype and the second, more robust method, perform competitively with state-of-the-art. They don't quite beat the scores from the best methods in literature, but they get pretty close. And we have the additional advantage of being able to explain anomalies. And I would argue that this is even more important in practical applications, because in order to be able to address the anomaly, we have to be able to intervene accordingly. And this is what explainability allows us to do. On the task of anomaly explanation, how the VQU-Net, so the second more robust method, performs better than the prototype as expected, because it has it's more robust to object appearance and it produces better quality of saliency maps. To get a gauge of how good the scores are, we can perform upper-bound analysis by taking, instead of the saliency map from VQU-Net, we can take the ground truth anomaly segmentations. This will test how good the method's ability to explain anomalies if it was given perfect saliency maps. As you can see, the scores from my method and from the upper bound are pretty close, which leads to two conclusions. The first one is that VQU-Net saliency maps are of good quality because the explanation scores you get are almost as good as if you had perfect saliency maps. This also leads to a second conclusion that explanation performance is currently limited by the state-of-the-art action recognition and object detection models available in literature. So in summary, I have developed a new dataset for benchmarking the task of anomaly explanations, and I have developed an explainable prototype to explain and detect anomalies. And this method was accepted one of the best machine learning conferences in the world. I then addressed the shortcomings of this method by developing a more robust but still interpretable method with performance on par with state-of-the-art, and while additionally being able to provide explanations of detected anomalies and better performance guarantees. I also concluded that at the moment, interpretable anomaly detection is limited by the state-of-the-art anomaly detection understanding in video. Thank you very much.
Thank you very much, Stan. This is a very interesting subject. I would like to say it's a very challenging one, and it's great to see the progress you made. It's a huge progress, and I think in such a short time, and it can be compared with the state of art. So this talk is now open to questions.
Yeah, hi, thanks, Stan. That's good. I think there's a whole bunch of applications in here, which are possible as well. And the video surveillance you've given is probably one of the more controversial topics to take on. But there's lots of industrial machine vision applications where anomaly detection is really the whole business. So I think if you're going to continue this, picking the right application space to do some sort of live trials could be great fun. So well done. It's a good space to explore.
Thank you. Just to address the kind of the controversialness of this topic in video surveillance, that's one of the reasons why the focus on the project was really on explainability and kind of really tackling the problems that could arise, exactly the controversy that, for example, the systems could be biased. But by having this explainability, I either try to tackle make sure that there is no bias, and even if there is, we have to know about it, which is why the focus was really on the interpretable part. But thank you for your point.
No, thank you. That's good, and it makes a good point about explainability, because there's explainability and explainability to whom, because some people may understand the explanation more easily than others, depending on their background.
Mm-hmm.
Any other questions? If there's no further question, let's thank Stan again and wish him every success if he decides to pursue along this direction. Thank you, Stan.
Thank you.
The next talk is going to be given by Rahul Swaminathan. And the title of his talk and his project is High Voltage Gallium Nitride Silicon Carbide Brushless DC Motor Controller for Solar Electric Vehicles. Rahul.
Hi, yeah. Can everyone hear me all right?
Yes.
Okay, let me just share my screen then.
Okay, I can see it.
Okay. Okay, can everyone see this fine?
I can see it, yes.
Okay, so yeah, hi, I'm Rahul. So my project was on building a high voltage gallium nitride traction inverter for solar electric vehicles. And to introduce the project, I'm going to show you Helia, which is this vehicle that Cambridge University Eco Racing built in 2019. And Helia is a 4-seater passenger electric vehicle, has a range of 900 kilometers on a full charge, and most importantly, has a cruising power of just 2,500 watts at highway speeds of 80 kilometers per hour. And to put that in perspective, that's the power that your average electric kettle would consume. And peak power consumption, going up hills and accelerating would be around the ballpark of 12 kilowatts. So this is an incredibly low power, high efficiency vehicle. And in 2019, we raced Helia across Australia in the Bridgestone World Solar Challenge. This is a grueling 3,000 kilometer race across the Australian outback. And there are only 2 charging points in the middle of this whole journey. And that corresponds to about 1,200 kilometers between stages at max. And unfortunately, in the event, Helia had to withdraw before completing the first stage because of one of our inverters failing. But nevertheless, we managed to go almost 1,000 kilometers, which was an admirable result, given that most vehicles entering did not even make it to the start line. But this did identify one major area of improvement, and that is the inverters. So the current inverters that we use in Helia are this one pictured here. It's called the Tritium Wave Sculptor 22. And there are sort of 3 main reasons why we want to change these and build something ourselves. First one is that the bus voltage of these inverters is limited to 160 volts, which in the scale of electric vehicles is relatively low. This introduces 2 main problems. Firstly, voltage sag. When the battery depletes to about 30%, our top speed then becomes limited to about 50 kilometers per hour, which is unsafe for highway driving. Secondly, we have increased I²R losses for the same power if our bus voltage is limited to such a low relative voltage. Furthermore, if we had an in-house inverter, it would allow us to add custom features, things like a cruise control loop or custom regenerative braking profiles. And this is something that we would want to implement in Helia. And finally, just as an organization, CVR is trying to disrupt the solar electric vehicle landscape, and the inverters present an excellent opportunity to do that through the use of wide bandgap materials, as I'll present. So when sizing the inverter, it was chosen to have an inverter rated for about 20 kilowatts at a bus voltage of 400 volts DC. Now, this figure was selected based on the fact that if one inverter fails, we still want to be able to drive the car, and we also want some overhead to perhaps scale up if we do increase the size of the vehicle in the future. And this corresponds to the switching devices needing to withstand 600 volts DC in the off state and about 60 amps continuous in the on state. So some of the devices that we considered, the first one was silicon MOSFETs, the cheapest and most widespread option. This has the benefit of being excellent in the switching performance aspect because it's a unipolar device, so we don't have this plasma to clear during the turnoff process. However, the on-state resistance is the main limitation of this device, and we can explore this using the classical silicon limit, which is based on a one-dimensional Poisson theory, which states that the drift region resistance, which tends to dominate the overall on-state resistance for a power MOSFET, is roughly proportional to the breakdown voltage to the power of 2.5. Now, it has been shown that this can be broken through devices like the superjunction, and this can be illustrated in this curve here, where the blue line is the classical silicon limit, and we have devices such as the Infineon CoolMOS, which is a superjunction device that then has decreased on-state resistance for the same blocking voltage that is predicted through the one-dimensional Poisson theory. So that was one device we considered, the classical silicon MOSFET. Still staying on silicon, we have the IGBTs, the insulated gate bipolar transistors. Now, these devices are a bipolar device, as suggested by the name, and because of that, we have this plasma built up in the on-state, which leads to conductivity modulation. And this significantly increases the on-state performance or decreases the on-state resistance of the device. However, the trade-off is now in the switching performance, as we then need to clear this plasma during the turnoff. And this slows down the device considerably compared to MOSFETs. And looking at devices, silicon IGBTs that fit that 600 volt, 60 amp range, I found that most of them tend to have an upper limit of about 20 to 50 kilohertz. And because of that limitation, I decided not to use silicon IGBTs for this inverter because I wasn't sure if I wanted to scale the switching frequency up even beyond that. So this is a good point to bring in the case for wide bandgap materials. So if you compare silicon carbide and gallium nitride using the Kang and Andrea figure of merit, which I'll show you in a minute, we can see that the wide bandgap materials offer orders of magnitude better performance in regards to on-state resistance and the breakdown voltage trade-off. And gallium nitride in particular is better for high frequency applications, and it is cheaper than silicon carbide given that we can grow it on a silicon substrate. So this last column here is comparing the figure of merit of silicon for each silicon carbide and GaN. And we can see that gallium nitride in particular offers vast improvements over standard silicon. and just visualizing the sort of physical properties of the three materials in this spiderweb chart, we can see that the blue line is silicon, and we have massive improvements in the high frequency and high voltage operation when we look at gallium nitride. So it was chosen to use gallium nitride, and specifically we chose to use the gallium nitride HEMT. Like the basic theory of this operation of this device is that we have this AlGaN-GaN heterojunction, and the lattice mismatch of these two layers creates a strain, which then leads to a piezoelectric effect. And then we have this piezopolarization effect, where we have a two-dimensional electron gas at this heterojunction. And this structure on the right is actually a depletion mode HEMT, but what we want in our inverter is an enhancement mode device, which is then built by using a PGAN gate over here. The reason we want an enhancement mode device is that we want the device to be normally off, and then we want to turn it on rather than being the vice versa. And the specific device chosen was the GS66516 by GaN Systems. So in choosing GaN HEMTs, there were some massive challenges that we had to overcome, especially in the gate driving aspect of things. And the first one is that the gate voltage is extremely sensitive because the maximum gate voltage that GaN HEMTs can withstand is about 6 volts. And this is dangerously close to the threshold voltage to turn on the device. So we can see here this the recommended range is about 5 volts. And then if we have any overshoot of this gate source voltage, we can accidentally damage the device. So in order to prevent this from occurring, we have to critically damp or overdamp the LCR resonance circuit at the gate drive turn on loop. However, there's another challenge in that we actually may want some undershoot and ringing in the turn off. And I'll talk about why this might be beneficial. But this means that we have to have different damping ratios for the turn on and turn off loops. And illustrating the two loops here, we have the green turn on loop and the blue turn off loop. And these formula here are just showing that we want the turn on loop to be critically damped or overdamped, and the turn off loop to be underdamped. So the other gate driving challenge that we have is this parasitic Miller turn on effect. So if our CGS, the Miller capacitance, is charged above the threshold voltage during a high dV by dt event, we can accidentally turn on the device, which would then lead to a catastrophic failure of the inverter. So there are a couple of solutions to this. The first one is to add an alternate current path through a sync resistor. And the second solution actually is why we may want the underdamped turn off loop, as mentioned before. And that is if we, and this is looking specifically at a half bridge configuration where we have two complementary devices. If we adjust the dead time between the two devices such that we turn on the complementary switch just at the point where the gate source voltage of its other switch is at its minimum, we can then prevent this Miller turn on from occurring by ensuring that the overall gate source voltage stays below the threshold voltage. And that's why we may want this to actually go negative, so that if this stopped at 0, then this may increase above the threshold voltage. So one gate driver circuit that was proposed is this one here. And the top half is just setting up an isolated power supply. But this uses a standard MOSFET gate driver and a digital isolator to ensure there's isolation between the low voltage and high voltage sides of the device. And we can see that we have two resistors here. This bottom one is for the turn on loop, which is why it's a higher resistance than the turn off loop resistor over here. Another issue that we had to overcome is this issue of common source inductance. And basically, we can accidentally turn on the device by a large DI/dt event by biasing the source. And the main solution is to use a Kelvin connection to the source pin. So actually, the device chosen, the GS66516, has a dedicated Kelvin connection to the source over here. But if we had a device that didn't have it, we can construct one in the PCB layout, something like this. And this is the common source inductance. It's common to the gate source loop as well as the main power loop. And the other issue that we want to tackle is EMI shielding of the device and parasitic inductances. And there are 3 PCB layouts that are compared in this. The first one is known as lateral layout, this one over here, where all the components are placed on the top side. And we then have a shield layer underneath the top layer with the components. And this has the benefit of being a single layer design, which is beneficial if we want to keep the cost of constructing the PCB low, and also make sure that we can have a more simple design. But this also means that the EMI shielding properties of this device is proportional to the thickness of the overall board. We can sort of overcome this by considering a vertical layout where the main power loop goes through the PCB as such. And this actually provides EMI shielding by having a magnetic field self-cancellation between the opposing directions of current. And because this loop is a lot tighter than this loop, that effect is more pronounced in the vertical layout. However, we basically have, the first layout, the EMI shielding is not dependent on the thickness of the board, because you can have an internal layer sort of just over here that is blocking the EMI from the main power loop. In the second one, it does depend on the thickness of the board, because the current has to travel through the entire thickness of the board. And also we have components on the bottom side, which just makes the design a little bit harder to mount and heatsink. We can overcome this by combining the best of both worlds in this hybrid layout over here. And as you can see in the table, we basically take the best aspects of both designs. Now, stepping aside from the power stage of the inverter and looking at the control stage, the main way we control this is through field-oriented control. So we basically have a demand current set point in the rotor reference frame, so the direct and quadrature components of the motor current. And in our case, we actually set the quadrature component to 0, because that provides us maximum torque per amp of current. And the way this works is we basically take a current reading. We then transform the 3 phase currents into 2 axes using the Clark transform. And this is still in the stator reference frame. Then taking the rotor position into account, we can then transform this into the rotor reference frame. And then that gives us our measured direct and quadrature current, and we run that through a PID loop. And then we just transform it back and then send the signals to the inverter through some PWM modulation methods, such as sinusoidal PWM, or in our case, space vector modulation. So 2 different motor control platforms were compared. And the first one is this ST motor control SDK. And this is mainly chosen because it supports FOC, and also the rest of the vehicle is using ST as the basis for their microcontrollers. And this supports Hall effect current sensing over here in the phase current sensing, which is beneficial because then we have an isolated way of sensing the current. However, so I built up this little control stage board, and I found out that it was actually very difficult to configure this board on their software. It was possible, but it's not ideal for training new members of the CUER electrical team. And this is actually quite a big consideration when implementing anything new in the vehicle, is that we needed to be able to be easy for new members to use. And that led me to try out the other platform, which is the Infineon iMotion platform. This does not support Hall effect current sensing, which means we do have to use a shunt resistor and then figure out the isolation afterwards. However, the configuration process is much easier, and this is a trade-off that does need to be made for CUER. So the Infineon control stage, there are basically 2 options. The first one is in using something like the IMC 300, where the Infineon chip is just supplying the control algorithm, and then we then pass the signals out to an external gate driver and an external power stage. The other option is to use something like the IMD 110 series, where we have the gate driver integrated in the IC. And the good thing about the GS66516 transistor that was chosen is that it's perfectly compatible with a regular MOSFET gate driver. The output voltages do need to be adjusted, but that can be done using something like a Zener diode to clamp the output voltage. So this is sort of the recommended control stage topology. Now, given that actually I did not have any lab access for this project, most of it was done on Plex to simulate the entire inverter, and the GS66516 devices did come with Plex models that were used. So this is the whole inverter, and this consists of three simulations. The first one is the electrical simulation, which is the field-oriented control over here, and then the power stage. There is also a mechanical simulation to look at the output torque and speed characteristics, as well as a thermal model to look at the heat dissipation. So these are just some waveforms from the output. Going bottom to top, the bottom one is output speed of the motor. So this was set at a demand of 100 radians per second. The middle one is just simulating a load torque applied after some operation. And the top is the product of the two, which gives the output power. So this just showing that we have a working speed control loop, and it does respond reasonably to a load torque. And then these are some simulations of the output current, phase current, and phase voltage waveforms. Now, the main thing we got out of the simulation is that we can look at switching frequency and relate that to losses and use that to determine what frequency we should switch the device at. So this is what we would expect from the device, where we have conduction losses relatively constant throughout and switching losses increasing linearly with switching frequency. And we can see that the overall efficiency does not drop much between switching at 5 kilohertz and 25 kilohertz. And this 20 kilohertz mark is about where the switching and conduction losses are about the same. And that leads us to choose this as a recommended switching frequency. And this is at a cruising output power of 2.5 kilowatts. We can also look at power output and junction temperature, and the heatsink was sized as per the recommendations from GaN Systems, which is about 1 joule per Kelvin thermal capacitance and standard values for thermal resistance between the junction to case and case to ambient. And we can see that even at 6 kilowatts, which corresponds to the peak output of 12 kilowatts shared between two inverters, the junction temperature rises to about 45 degrees, which is still acceptable at an ambient of 25 degrees. So summing it all up, and this is the actual device. So I had these little half-bridge boards, but unfortunately, without access to labs, there was no way to actually construct the power stage and test it out with a real motor. But to conclude, the final recommendations from CVR that were gained from this project is, first of all, to use the Infineon control stage with the custom gate driver. So as mentioned before, this one here, where we have the custom gate driver instead of the integrated solution. And that was chosen so that we have full control over the turn on and turn off damping ratio. Also to use the hybrid PCB layout for EMI suppression, and selecting a switching frequency of about 20 kilohertz from based on the Plex model. However, this figure does need to be validated experimentally, and I'm hoping to return to Cambridge once lockdown situations ease in Singapore, where I am, and actually construct this inverter. Finally, there's also a model of the transistor, the GS66516B, which is this one, which allows for bottom side cooling for the device. So these PCBs here are actually aluminum substrate ones, so we can have heat sinking done through the PCB and have a larger cold plate at the bottom. And this allows for having actually a double-sided heatsink design, which would save on the overall footprint of the device. Thank you.
Thank you very much. This is a very comprehensive overview of the projects and what has been achieved. And I can see is very much in the current interest how you can provide a power controller for large power, especially for electric vehicles. So in the interest of time, we could have one quick question if somebody would like to ask Rahul. No? So in this case, Rahul, thank you very much. That was a very nice talk.
Thank you.
And we are now move on to the part for the Blue Sky research presentation. The Blue Sky research, as I explained, is a 6-month research sponsored by CAPE partners and is aimed for the postdoctoral research associates, and they want to develop their own ideas and with some independent research. The first talk will come from Dr. Jin Li, and the title of his talk is Large Field of View 3D Holographic Displays Using Wavefront Shaping of Multiple Light Scattering Fields. Jin.
Yes, I will share my screen.
Thank you.
Yes, Professor, can you see my screen?
Yes, I can see your presentation. Yes.
Yeah. Let's start. Good afternoon, everyone. I would like to talk my Blue Sky project. In my project, I would like to investigate a new large field view 3D holography display approach using wavefront shaping of light scattering fields. The holographic display can precisely tailor light fields. It can be capable of resembling realistic 3D scenes with full motion parallax. As shown in this figure, a CGH algorithm can generate a hologram with all depth cues. When a laser beam illuminates a hologram presented on a spatial light modulator, arbitrary diffracted wavefronts can be generated. A viewer can directly observe a 3D holographic image. In this 3D image, the full 3 visual depth cues can be delivered. Currently, holographic display can be also considered as the ultimate 3D visualization technologies. Holographic display can have great market potential for various applications. Here we list several application examples, such as holographic AR, VR, holographic medical data, holographic interactive display, and holographic 3D maps. To develop a high-quality holographic 3D video display, 3 essential elements are needed. One is a wide-angle optical system. Another is the high-bandwidth SM. And the third is the fast computer generation hologram algorithm. Some advanced spatial light modulators, like fast LCOS spatial light modulators and optically addressed spatial light modulators, have been investigated. Current multiple fast hologram generation algorithms, like the layer-based algorithms, have been developed. My project focuses on a new approach for wide view angle holography display system. So my talk has 3 parts. I'll start with our research background, which involves issues in holographic displays and existing methods and our project objective. Then we will talk about our approach from principal experiments and discussion parts. Finally, I will conclude my talk. In holographic display fields, there is a fundamental research problem. The information content of a hologram is much greater than the display capability of current spatial light modulators, because a current SM has a low pixel pitch and a small area. The current system can only provide a holographic image with a low space bandwidth product. The SM system can't completely display a large space bandwidth product hologram. Here, we list the comparison between the hologram information SM capability from pixel pitch, hologram size, view angle, and optical extent. We can see that the optical extent of the hologram is almost 3,000 times larger than the SM capability. This means that the current SM can't match the CGH information. So an efficient holographic display method is necessary for the current holographic video with a large optical extent. Currently, to adapt to a large optical extent generated by a hologram, multiple 3D hologram display systems have been proposed. For example, MIT utilized a LM modulator in conjunction with a horizontal polygon scanner to achieve the holographic display. With it can achieve a large field of view. The TUAT group also adopted a high-speed SM and one-dimensional horizontal scanner to obtain the same result. Simple A-star company utilized 24 physically tiled SMs. They are used to optically scanning tiling method to develop a fully parallax digital 3 holographic display system. They also integrated two sets of RGB lasers, allowing full color displays. My colleagues Jia and Jin Li utilized the tiled grating and the vertical diffuser to implement a scanning 3D color video display to manage the required optical extent of holograms. In my previous works, we developed a coarse integral hologram display concept. This concept involves a static stage, dynamic stage, full bandwidth stage, and scalable stage approaches. The principle of the stage display is that several low space bandwidth product holograms are angularly tiled using coarse integral optics. This method would like to form a modest size and wide field of view display. By fully utilizing the bandwidth of SM, we got the best holographic display approach, which is developed to improve the image size and the view angle. Accordingly, we utilized our previous full bandwidth stage method to construct a holycube system. This system adopts a cube structure, and all components involving optics, electronics, and mechanics are packaged into this cube structure. A viewer can directly see a holographic image. This holycube system can achieve a view angle of 40 degrees. This system can display a color holographic video, and the frame frequency is 24 Hz. Alternatively, in this project, we would like to develop a new holographic display method based on wavefront shaping of light scattering fields to augment space bandwidth product. Using a wavefront modulator in conjunction with a highly disordered medium, we generated a dynamic holographic image with significantly increased both limited view angle and image size. In common approach, so in this figure A, for a single wave modulator like spatial modulators, deformable mirrors, and digital micrometer devices, the product of image area and view angle is constant at a given wavelength. For example, in a Fourier holographic display system, when we use a physical or virtual transform lens has a large focal length, the system will produce a large image area with a narrow view angle. Inversely, when we use transparent lens having a smaller focal length, the system will provide a view angle. However, this is achieved at the expense of decreased image area. In our approach, shown in figure B here, we utilize a complex media to replace the transform lens. We found that the relationship between the image size and the view angle is broken because the light scattering field results in the complete mixing of spatial frequency. Accordingly, this mixed effects can produce volume speckle fields, which cannot be directly used for the displaying image by itself. So we utilize the wavefront shaping to explore the random speckle fields for 3D holographic display with a high space bandwidth product. To validate the proposed concept, we experimentally demonstrate the enhancement of the space bandwidth product by generating optical focus. As shown in this figure, optical setup involves a forward path and backward path, which consists of a wavefront modulator, 4F relay optics, and a tube media lens, and imaging system, and a host computer. To generate the optical focus in a light scattering fields, the wavefront modulator modulating a wavefront impinging on the scattering layer, and the imaging system measure the cross-boarding 2D images on specific focal plane, which is utilized to perform the interactive feedback algorithm through the backward path. This slide demonstrates our experiment setup, which include a software control platform and optics. The optical configuration and composed of laser optics, a waveform modulator, 4F relay, and a camera. Here, we demonstrate the image results when a disorder lens is used, but without waveform shaping. The scattering fields cannot be imaged. When a disorder lens is used, but with the wavefront shaping, the scattering fields can be imaged. This results indicate that the wavefront optimization can produce a tightly focused spot in the desired position. So the shaping of the light scattering fields can be used for the display. We also analyze the spaceband product of our approach. Here we provide the calculation equations of two methods. The only wavefront modulator method utilizes the product between the wavelengths and the pixel number to calculate the space bandwidth product. Regarding the wavefront modulator injection and the disordered medium, we use the input beam width, diffusion angle, and the diffusion distance to calculate the space bandwidth product. Based on these equations, we can see that our method can significantly improve the space bandwidth product compared with the case of using wavefront modulator. Finally, I will conclude my talk. To sum up, we talked about fundamental issues of space bandwidth products that exist in current holographic display system. Accordingly, I also introduced several advanced holographic display approach and our previous stage method. Then I demonstrated this project approach involving simple experiment setup, imaging results, and the space bandwidth product comparison. In future, we would like to go to a intersection to combine our approach with our previous stage method by utilizing large pixel number wavefront modulator like LCOS SMO and DMD to achieve a photorealistic three-dimensional holographic video display. Well, that's all presentation from me. Thank you very much for your attention.
Thank you very much, Jin, and for the talk on a novel approach and on the important application. So the presentation is now open for questions. So, Jin, I just wondering,
yes.
You have made some of initial trials and show the success and the feasibility.
Yes.
Is any plan you would like to consider taking to more detailed, high quality applications?
Yes, yes. And yeah, and one is the direction we can use combine the my current disorder media to replace the my previous stage display. And this we can do reduce our system volume because my current disordered method can reduce the optical complements for a holographic display system. Yeah, in future, I would like to investigate integrated holographic display system. So if I can directly use this method to improve my previous results.
Sure.
Yes. Thank you very much.
Sure. Is there any other questions? If not, let's thank Jin again for the nice talk. Thank you, Jin.
Thank you.
We are ahead of time, and the next talk is going to be given by Dr. Pawan Shrestha. And the title of his talk is Multi-Stable Terapixel OASLM for the Updatable Holographic based on 3D display, or for the 3D display, yeah. Okay, Pawan.
Can you see my screen?
Yes, I can see the screen. Yeah.
Hello, everyone. Thank you for this opportunity. I'm really honored to share my research with you today. And the topics of my talk is multi-stable terapixel OASLM for updatable holography-based 3D display. And today I will be talking about the background of OASLM and the experimental setup and some results. The work done for this Blue Sky Award is based on 3 years of research we have been doing in our group before the award. So the results haven't been published yet, so I won't be able to disclose all the details of how we arrived at the device, but I will try to show you some results. The spatial light modulators, or SLMs, and these the primary function of SLMs is to modulate the readout beam. These examples of SLMs include OASLMS, or electrically addressed SLMs, and OASLMS, which are optically addressed SLMs. And these OASLMs are like these computer screens. So, as the name suggests, the addressing is done electrically, and they have rows and columns of addressing matrices. And when you select a particular row and particular column, particular pixel is selected, and once you apply voltage on the pixel, the adjacent liquid crystal changes its orientation and modulates the readout beam, and hence we see the image. In optically addressed spatial light modulator, addressing is done optically. So here you can see there's a photosensor layer. So when the image is incident on the photosensor layer, it changes the charge distribution on the photosensor layer. And there's the voltage applied between this photosensor layer and liquid crystal layer. So when the charge distribution changes on the photosensor layer, the liquid crystal layer changes its orientation, and the output light or readout light is modulated, and we see the output image. In case of OASLM, there's no need for the transistors or even pixelation. So it is suitable for, it can provide high resolution, a bit easier than in OASLM, and is suitable for holography-based display because it doesn't have any unwanted diffraction pattern from the pixelated nature of the device, as it has in OASLM. Similar to that OASLM, we developed optically operated spatial light modulator, which we call OASLM. In this case, there is no electrical control required as in OASLM, so it's completely optical, and it switches with a high speed and can provide quite high resolution as well. So the target of the project was to create a really large display with very high resolution, and this is the OASLM we developed during the project. You can see it's quite large, nearly 1 meter square. It's 1200 millimeter by 700 millimeter on the side, and we use laser to write. So this is a write laser which is collimated, and we use a hologram mask to pattern or using contact imaging to stamp all over the OASLM. So the hologram mask used is developed by Jin Li, who was a member of, and it's basically a hologram of a dragon with different views in tiled angularly with a depth map, so you can get the 3D feeling of the, or it has a 3D effect
And this is me holding this O2SLM, and we have a rig laser, and it passes through the O2SLM, and we can see the hologram. Yeah, I'll show another result. And this is as we move the laser from side to side on the O2SLM. I just took a small part of it. We wrote almost everywhere in this device. So you can see the dragon, different points of the dragon on the device in this case. The pixel pitch of the previous hologram was 2 micrometers, so I wanted to make it exactly like a terabit. So I developed another hologram mask using a similar algorithm calculation as Jin Li used. And this is 0.75 micrometer pixel pitch. We didn't manage to write it on the O2SLM, but we managed to develop the mask for the project. So ideally, when we use mask, it was just to prove the concept that we can make a big OSLM, big O2SLM, and then it can be written all over the O2SLM. But if the downside of that approach is the viewing window is limited to the viewing window provided by the mask, because it's just stamped same thing over and over again. So ideally, we would like to develop image writing system. So this is the writing system consists of DMD, and we demagnify the DMD. So it has a laser. So as shown in the CAD model, we have a laser which is collimated and goes to the DMD, and then it focuses onto the O2SLM, which will be placed underneath. The concept behind the experiment is quite not that complicated, but executing itself is proved to be quite a challenge, because lots of different problems and the developing this mechanical frame. We did manage to do that. Actually, Dr. Matt Tran developed this part, and the writing mechanism, Matt and myself developed the writing mechanism. So this image engine called this moves from side to side, and this rolls over on the this side. So we can put the O2SLM on this optical breadboard on very sturdy table. And the idea is now, if we can calculate giant hologram, we can write it, say, 1 micrometer pixel size by demagnification, something like that. And it should provide a single big hologram. The motors we used are stepper motors and controlled by Arduino. However, the whole mechanism is not functional or not complete yet because of the starting issue. So we are yet to complete and run this part of the project. That's the work I did for this Blue Sky work. Thank you very much for your time.
Thank you, Pawan, and thank you for the talk. And it's a heroic effort to try to push the boundary and try to accommodate the larger information bandwidth using an optical engine. And now the talk is open to questions.
Thank you very much for the presentation. And I do have a question, but I'm not sure whether it's a dumb question. So what is the purpose of, or what is the application for the for your spatial light modulator here?
So the idea is, like, when we look at these holograms, they are quite small. When you view the hologram, it's very hard to look at the hologram because it's quite tiny or small. But if we were just my friend Matt and myself were sitting and we were thinking like, what if it was really, really large and it had a really large viewing angle as well? So it's just to create big hologram which can be updated. It's not actually, this is updatable. So ideally you could write it with light, and then you can just change the hologram as well. So if it is fully functional, we would imagine you would have a window size hologram through which you can see gigantic dragon.
Okay, because this hologram is not my, well, definitely not my field. I'm trying to put it into concept because we've seen a lot of hologram in the sci-fi movies like Star Trek, Star Wars kind of thing. So are you trying to make those things into real life? And also when you say, because they're small, and now if you make them bigger, does it mean that it also show more details, or it's just a simple, like a digital zoom out kind of thing?
It's not like a digital zoom out kind of thing. It's like these are fundamentally limited by pixel pitch and size of the its space bandwidth product, which is like so we have different technologies to display holograms, say LCOS or DMD. These are in this case is like 1 inch display, around 1 inch display. And you have fixed number of pixels on them, which are say 3 micrometer pixel size. And so this provides you field of view or viewing angle of 7 degrees, around 7 degrees. 7 degree means it's very, very narrow. You have to be in position to see. You cannot see large image as you would see through the window or real, like a computer screen. You could not see it like that. It's quite narrow, small image you could see. So there is a way to make the viewing angle large. So you could optically demagnify or with pixel pitch. So you put lenses around it so that you can make the pixel pitch look smaller. So say 1 micrometer or slightly smaller. Then the viewing angle increases, but the viewing window itself becomes very small. So you have to be exactly positioned in precise position to look at it, and it's very difficult to see the hologram. But using the device like which we developed, in this case, you could have a really large window to look through, and pixel pitch also can be very, very large. So you can see very big objects. Otherwise, even if you have large device, the object you can see can be very, very small. So it's like it's a hologram, but it's a bit underwhelming. But when it really hits is when you have really big lifelike thing, like what you said about sci-fi movie, similar to that. Like when you go in there, you get confused or you see the things moving there.
I see. So does it mean that the thing we see from the sci-fi movies, like, you know, the images that they put up there is not actually accurate to demonstrate?
There are not using really hologram techniques that we discussed about. There are tricks to doing it, like they call smoke meter or other. There are different tricks to do it. So or computer like post editing or other things to do it. Not so far. This kind of moving image is not possible yet.
All right. Thank you.
Thank you for your question.
Thanks. Any other questions?
If not, I'll ask another.
No.
So you did measure. You did mention that it'll be ultra fast, right?
Yes, it is fast.
So first of all, I have very limited knowledge in your field, and I'm just trying to piece everything together. And my question is that, so what is the bottleneck of the speed? Like, What limits the speed?
Several factors. So in device itself, it's like, first of all, the photosensitive thing which we use, they need to respond really fast to light, and then they need to have a there is another layer, liquid crystal layer I mentioned in you can see it here. So we have layer, the speed is limited by photosensor layer, and then liquid crystal layer. It's just a mechanical speed, like a viscosity. It has a viscosity and it cannot respond really quickly. In our case, the photosensor layer is fast, but it is still limited by liquid crystal layer speed, which is still enough to give video speed. Yeah. Other things could be calculating of such hologram itself is quite slow.
So when you say very fast switching, how like what time scale are you talking about?
Milliseconds. It's the material itself can switch much faster than that. But when we put it into device configuration, we're talking about milliseconds.
Okay. So, and the other thing that I would imagine here is that when the arrow says read out light and then output image. So I imagine there would be computing process involved.
Yes.
Will that be a limiting factor? Like is it demanding for the computing power or?
Yes. So the input image would be computed to. So this part is not. There's no computation involved in this.
The other side. Sorry. Okay.
But
so you do need a really powerful computer to do this.
Yes, it is a challenge. It's a big challenge.
Thanks.
I think this is probably a topic of a common interest. I would like to add a bit comments on it. So the aim is to get a large 3D viewing the images and of high quality. And intrinsically, they need a lot of information, probably 3 orders at least more of the information than what we see on the 2D image. And that's create a lot of problems, not in the fundamental physics. The holographic fundamental physics is capable of being able to do it, but is how to generate the information itself in the holographic way to process such a large amount of data. So we're talking about a terabit per second data in a raw data form. So the calculation is one of them. For holography, you can do on the 2D on fly, which means in a real time, like 30 or 60 frames per second with the high definition television 2D. That's possible, full color. But for 3D, we're not there yet. So that's one thing. Then you've got the information source, then you have the hardware to have the data bus to pass through it, to feed into your display engine, which again, the current hardware data bus can only support the 2D display, not the 3D. So we have to do hardwiring the data streaming part, not to go through the current data bus controller. Then you come to the optical engine, which is where this talk is focused about. The optical engine needed to be able to deliver the high information bandwidth, so you need a large amount of data pixels. And at the same time, to be able to give you a larger field of view as well. So the larger field of view is limited by the optical diffraction, which is in the holographic is a diffractive optics. So the smaller pixel feature give you a large field of view. But currently the optical engine can only give you a field of view about 1 or 2 degrees. So if you want to be like the normal display required to get to the 60, 90, or 120, even 180 degrees viewing. That's still far away. And also, the current optical engine, or what we call spatial light modulator, can only give you a very limited bandwidth because it's designed for 2D. So all the practice given is a small image with a small viewing angle. The image is small. If you want to have a high quality, you have to use a microscope, optical microscope, to see it. So that's certainly is not satisfactory. So the effort here is to try to make a holographic display with a larger size at this project, which you need a large amount of data. So terabit pixel data, then you can see a large scale up holographic display. Then how to update the faster, and there's a material limitation, which are not really limiting here for the normal viewing, but it is the device itself, how to updating it, and then how to upload the data in a real time. So that's still remain to be solved. So currently is only limited to updatable, not video 3D display yet. So I hope that answers your question.
Thank you so much. I definitely learned a lot from that. Thank you.
Okay, any other questions? If no further question, we'll conclude this session. And we thank Pawan again for the very nice talk. And thank you everybody for participating wherever you are. And see you next time with the next round of the CAPE Acorn Founder Winner presentations.